We had some homework last night, page 453, 1 to 2, 5 to 9, and question 11. I want to take a look at question number 7 right now, a great question, which says a Mexican jumping bean moves because an insect larva inside the shell wiggles. Would it increase the the motion to have the mass of the insect greater or to have the mass of the shell greater? Let's take a little vote on this here before we give you an answer here. Looking for commitment from you guys. Okay. How many people think it would increase the motion to have the mass of the insect greater? Okay, how many people think it would increase the motion to have the mass of the shell greater? And nobody wants to raise their hand now because so many people raised their hand before. It's okay to go out on a limb. Sometimes the minority is right, you know.
Sometimes.
The answer is the insect. Okay, the minority or the majority was correct here. You guys were correct in this. Can anybody give me a good reason why, if we want this thing to increase its motion, why it would make sense for the insect's mass to be heavier or to be greater as opposed to the mass of the shell being greater? Nick? Okay. Yeah. Can we? And that's good. Okay, it's a good start to that answer there. Yep.
Since like the insect is the driving force that's wiggling around, giving it greater mass.
Okay, good. That's what I was looking for is that word, the momentum word, the M word in there, right? So if, exactly as Matt said, if the insect has more mass and it's wiggling around with a certain velocity, it's going to have more momentum, right? If you got an insect moving around with a velocity of, let's say, 1, we'll just say 1 unit for ease of math there, okay, and its mass is 2, okay, then its momentum is 2. 1 times 2 is 2, right? Okay, if its velocity is 1, but its mass is 5, then its momentum is 5. You want the insect to have the momentum. The one that's doing the transferring, you want to have more momentum. Okay, so you do that by giving it more mass or by it having more mass. The insect has more mass, it has more momentum to transfer to the shell, and then the shell starts moving. Now, if the shell is heavy when it starts moving, given a certain amount of momentum, it's not going to be moving all that fast. If it's given the same amount of momentum from the insect, then and it's got a lower mass, then its velocity is going to be higher. Does that make sense? So the idea is in the shell, give it more mass, give it more momentum. Now, that's for the insect. For the shell, the idea is the momentum you gave the insect is the momentum the shell gets. You want to decrease the mass of the shell so that the velocity of the shell ends up being higher to keep the momentum, whatever it was that was given to it. That make sense? That's a good question. Yeah, how many of you guys, I mean, lots of you guys got the answer correct, but how many of you guys got more or less the explanation of that correct? Okay, good. That's a good thinking question. Okay, it's a good question because it isn't just straight from your notes kind of a question, right? You did have to think about that and understand that. All right, good. Okay, any other questions there from that homework last night? 1, 2, 5, 6, 7, 8, 9, 11? No? Okay, what I'd like to do then is give you a few minutes, not a great deal of time, but a few minutes to work on the remaining portion of those questions, which was 13 to 16. And that's going to include a couple of those variable value changing questions that we took a look at on Friday. Do you guys need to do another one of those as an example, or do you just want to tackle those questions right now and see how they go? Okay, so we'll give you a few minutes to tackle those, see how they go, and then maybe about 10 minutes, we'll take a look at 1 or 2 of those questions if we need to, all right? All right, number 14 says, a jet flies west at 190. What's the momentum of the jet if its total mass is 2,250 kilograms? This is a pretty straightforward question, number 14a. All we're going to do is say P is equal to m times v. What is it? 2,250 times the velocity of 190. Now, it does say it's 190 to the west. So we either have to think of west as positive or negative, or remember to use the word in our answer here. 2,250 times 190 is what? Does anybody have that calculated? It is 4.28 times 10 to the 5. And that would be kilograms meters per second. And we're going to want to specify west here unless we specified earlier that positive was west. Does that make sense? You got to indicate the direction somehow, and we hadn't until we wrote the word west down because we hadn't specified anything ahead of time as to what the direction meant. So done. Hardest part of that is the direction. B says, what would the momentum of the jet become if the mass was 3/4 of the original value and the speed increased to 6/5? Now, somebody asked a question as I was walking around. Can we just take 3/4 of the mass? Because we have the value, right? Take 3/4 of the mass and then take 6/5 of the speed or the velocity and do it that way? Yeah, you could. You don't actually have to use this variable value changing technique to solve this question, right? But because at some times we're going to have to use variable value changing, that's how I'm going to solve this question. So I'm going to say, if you remember from Friday, my original value is equal to my equation. Now, my original value is also equal to, 4.28 times 10 to the 5? That make sense? Pretty much my givens, right? Here's my equation that I'm given on my data sheet. Here's the number that I'm given from question A. Now, my new momentum is, well, it's still mass times velocity, but the mass isn't m anymore. The mass is now 3/4 m. So we're going to say 3/4 m for our mass. The symbol was for mass was m. The symbol for mass is now 3/4 m. And velocity, well, it was v. Now it's 6/5 of v. Now let's simplify this a little bit. 3 times 6 is 18. 4 times 5 is 20. So we get 18 over 20 times m times v. And we already know what that is. M times v is 4.28 times 10 to the 5. So I'm going to say 18 over 20, or 9 over 10, times 4.28 times 10 to the 5. Taking 90% of that value. And when I do that, I get 3.85 times 10 to the 5 kilograms meters per second. All right? How many people did it my way using variable value changing here? Okay, a handful. How many people actually just took the value of mass and velocity and did it that way? Listen, that's fine, right? But just be aware of how to do this in case you weren't asked question A, in case you didn't have the information from that question. Yep. That's a good question. Yeah, you would actually. Yeah, absolutely. I missed that. But you would, because it asks you for the momentum, and momentum's a vector. If they ask you for the magnitude of the momentum, or they didn't give you any indication of direction, then there's not much you could do there, like on some of the questions on our worksheet, right? But if we have a direction and they ask me for momentum, then I have to give it, yeah. So 3.85 times 10 to the 5 to the west. Or if earlier on I had have defined west as positive, then I could have gotten away with just leaving it as positive. Okay. Good. Do you want to do another question? Are you good, or do you need a little bit more time to work on that? Oh yeah, let's take a look at another example. This is example number 4, and this is on the example handout that I gave you last week. It's the last one at the bottom of the page. Doesn't look too hard. Find the momentum, find the kinetic energy of something, but there is a little bit of a twist here you're going to see in a couple moments here. Example number 4 says a 1,000 kilogram car travels at 10 meters per second, and a 1,200 kilogram truck travels at 12 meters per second. What's the momentum and the kinetic energy of the system, not of each object, but of the system? If the car is traveling north and the truck is traveling south, then B is different directions here. We'll worry about A first. If I want to find the momentum of the car and the truck, then I have to add up the momentum of each object. Make sense? Car has a momentum, truck has a momentum, add them up. So I'm going to say the total momentum here is m1 v1 plus m2 v2. Does that make sense? Momentum 1 plus momentum 2 gives me the total momentum. Mass 1, we're going to say, is 1,000 kilograms, and its velocity initial, or its velocity, is 10 meters per second. The truck is 1,200 kilograms, and its velocity is, what is it, 12 meters per second? Is that right? Negative, good. Okay, you can see that I left a space there to put in the negative. Why is it necessary, Kelly, to put the negative in there for the velocity of the truck? That's right. The car is going to the north, and the truck is going to the south. Momentum and velocity are vectors. Well, they're different, yes, but they're vectors. So if they're vectors, we need to include direction associated with it. Okay, so what do I got? 10,000 times 10 is 10,000. 1,200 times 12 is 144, 14,400. So it's going to give me, I believe, negative 4,400. Is that right? And that would be kilograms meters per second. We should really round that to 2 digits. Negative 4.4 times 10 to the 3 kilograms meters per second. A little bit different than other questions we've done to this point because we've had to combine the car and the truck together. But I don't think that's a big jump from what we've already done, right? Just find the momentum of two things combined. I'm going to change that subscript to P total instead of PT because I don't want you to get mixed up and think it's the momentum of the truck. Okay, it's the total momentum. Now let's find the total kinetic energy. You guys remember the equation for kinetic energy? Check your data sheet if you don't. You find it in the bottom left-hand section of your data sheet. Kessler kinetic energy is? Right. Now there's two objects here, so we're going to say 1/2 m1 v1 squared plus 1/2 m2 v2 squared. What's the second mass? 1,200 kilograms. Don't forget to square that. Am I missing something here? Oh, I tricked you by leaving that space, didn't I? There's no negative there. Why would it be negative 12? Oh, because it's to the south, right? Except that we're not looking for velocity and momentum. We're looking for speed and kinetic energy. And speed and kinetic energy are scalars, right? So we don't include any direction, no matter what they are. 10 squared times 1,000 is 10,000, 5,000. Plus 12 squared is 144 times, oh, I don't know what that is. We get 86,400 there. Oh, yeah. I don't square 5,000, but 10 squared is 100, 100,000. This is 50,000, right? Right? 50,000 plus 86,400 gives me 136,400 joules, or 1.4 times 10 to the 5 joules. Okay? So there's a little bit of a trick there, hey? A little bit of a trick, not too much. Just remember that momentum is a vector, direction always matters, kinetic energy is a scalar, direction never matters. Right, Cameron? Okay, let's take a look at B. This time the car is traveling north and the truck is traveling west. Does it change anything? Sure does with momentum, at least. How come? Because direction matters for momentum, right? We've changed direction, and direction matters. Here's what I want to do for B. We got a car, draw a diagram here. A car that has a mass of 1,000 kilograms and a speed of 10 meters per second going north. And then we have one going west that has a mass of 1,200 kilograms and a velocity of 12 meters per second. And then they crash into each other. Good. So the momentum of this one, 10 times 1,000 is 10,000. Agree with that? The momentum of this one is, what, 12 times 12 is 144. 2 zeros, 14,400. What do I do? Add them up, 24,400? What do I got to do? Yeah, Kathleen, let's change that into a vector diagram first. This is what I call a situational diagram. Situational diagram just kind of shows us what's going on. Okay, does that make sense? A vector diagram, on the other hand, is going to be drawn so that the vectors are head to tail. So we draw one like this, head to tail. 14,400, 10,000, and we can find the magnitude of the momentum and the angle by doing the Pythagorean theorem. And we can find the angle by using the inverse tan function of opposite over adjacent. Opposite being 10,000, adjacent being 14,400. All right, what do we get for the momentum there? You get 1.8 times 10 to the 4. Kilograms meters per second. And our angle is at 35 degrees north of west. How come we had to include that angle there? Because it's a vector. If there's a way to find direction, we've got to include it. Do you understand the difference between the blue question A and the blue question B here? Like, we found the total momentum completely differently, in a sense. But in one sense, we did the same thing. In both questions, we added together the vectors. But in question A, because they were both on the same plane, north and south, we added them together the old-fashioned way. In question B, because they were on two different planes, one was north, one was west, then we had to add them together using the Pythagorean theorem in a vector diagram. I will give somebody out there a really, really big prize, which the prize, by the way, will just be my admiration for you. But that's really big. If in 3 seconds or less, you can give me the answer for the kinetic energy for B. Same thing as what? Good. 1.4 times 10 to the 3. Sorry, times 10 to the 5. You've earned my admiration now. Hey, why is it the same thing? I didn't have to do anything with vector components or x and y's or Pythagorean theorem or the inverse tan function for kinetic energy. How come? Because direction doesn't matter. Not only does it not matter, not only do we not need to use direction for kinetic energy, we can't use direction for kinetic energy. If we try to do this kind of analysis for kinetic energy, we're wrong. You can't add scalars that way. Okay, with scalars, 3 plus 4 is equal to 7. Right? When you're adding 3 plus 4 as right-angled vectors, 3 plus 4 is equal to 5. It's two different answers, right? One is right, one is wrong. When we're adding vectors, 3 plus 4 would be 5. When we're adding scalars, 3 plus 4 would be 7. Right? All right. What I'd like to do with you right now is just show you something. Um, we tomorrow's Wednesday. We're gonna have ourselves a quiz on momentum on Thursday. Okay, and the day before every quiz, we're gonna have a peek at some practice questions to kind of help prepare you for that quiz. And those practice questions are going to be posted on Google Classroom. They're actually posted for you already on Google Classroom. When you go onto Google Classroom, you will see, I'll go to the right class here. Scroll down a little bit here once this internet does its thing. If the internet would work, then it would have taken us to our classroom page, which right now would have listed two things. One would be practice question set number 1, questions, and then you would see a separate entry that would be practice question set number 1, answer sheet. Okay, you would click on the questions to see 4 multiple choice questions, which are questions from old diploma exams, the first 4 practice questions from old diploma exams that you've seen this year. You click that, you open it, and you look at the questions. You do them. And then the other entry is the answer sheet, which you'll click on and then submit to me on that electronic answer sheet the answers that you got. They don't count for anything except practice. We'll go over them in class tomorrow, and then we'll have a quiz on Thursday. That's what we'll do every time before a quiz. Okay, we'll do practice questions one day, like say on a Tuesday. We'll check them over the next day, and then the third day we'll have our actual quiz on the same material. It won't always be the same exact type questions, but same type of material. So hopefully you'll be a little bit more ready for that. Yep.